Well, welcome everybody. This is Jeff Crosier again, Senior Principal. This is part 2 of the Introduction to Seismic Retrofitting of Reinforced Concrete and Masonry Structures, also unreinforced masonry structures. So this is I'll pick up where we left off with the last presentation for those who were there, and some probably weren't there. So this is it's all supplementary. You can watch the first part on video. And get the slides to change. There we go. So unreinforced masonry buildings. Obviously, the first point of weakness is wall anchorage. Walls are very brittle, they're very weak, and they're older generation buildings where the seismic response of building wasn't well understood. So some of the tricks that are key is actually anchoring the diaphragms, the floor and the roof diaphragms to the walls to provide stability to the walls. Because usually what's happened in earthquakes, ever since these buildings were new, the walls will shake. They're a completely different response from the roof diaphragms, and then they let go, and then the walls collapse as they become unstable. Here we've got some details that have been used successfully throughout the past to anchor either the trusses or when we have parallel joists, strapping and anchors. So we use those to tie the two things together. I'm gonna kind of keep this at a high level, not very detailed, but I just want to make sure you see what the options are and what the possibilities are. This is kind of more similar details if you have just sawn lumber joists. Actually, the picture in one on the left is kind of common because the way people used to build the buildings, particularly in California, an unreinforced masonry building, they would leave a pocket for each roof joist, or floor joist. So you'd see a 2x12 sitting in a little small pocket. So they're basically tapered into the pocket, and that was the whole connection of the floor to the roof. There was no positive, out of plane connection. So these details kind of, do a good job of starting to tie all that stuff together.
Hey, Jeff.
Yes.
A couple of comments here. The taper cut is there. It was called a fire cut. And the reason there is that if there was a fire and the joist burned out and they lost support, then the joist could rotate out of the wall without pulling the wall down. So that's why they were historically like that. The other thing to note is that the anchors on the top, so this is really common. You get a reduction in thickness. It could be at any floor, but it's certainly almost always at the roof. And that serves as a parapet. And the roof, and sometimes those walls are only 9 inches thick. And so those anchors that we're showing right there, those 22.5-degree anchors, they're not really technically approved for 9-inch thick. It's like a 13-inch minimum. We've used them in the past, but the preferred way is to go through the wall on those.
Yep. True story. We would use those in Southern California. They had reduced value, so you used to have a lot more of them in a 9-inch. Lon's got a good point. Masonry walls they're brick. They're either 9, 13, or 17. They go in courses of 4 inches, depending on how many wides of brick there are. But yeah, typically in the South, we would anchor those directly to the centroid of the joist and go through whatever that blocking piece is, and not have a top and bottom. But anyway, there's many ways to skin the cat. Seems really weird. This is an example of, in Yusuf, this is, I think, some of the work that came out of the seismic retrofit we did with Istanbul, and maybe Lon knows about this. I think he was involved in that too, where, I think we started with 1,000 buildings, 1,000 school buildings that we wanted to retrofit. They had a limited amount of money and they wanted to do minimal, they wanted to touch as many buildings as they could with the amount of money they had. So we came up with some rather simplistic, but, good performing systems to make those buildings significantly better. And one of the things was to shotcrete or add concrete to the outside walls to add shear strength, and then also do the wall and roof anchorage. So this is kind of a good way to do that. It's pretty, like we talked about last week, it's kind of the brute force, simple, but very effective method. And then here's some of the details of all that, where these are actually, Existing floors. These are existing floor joists that are anchored through the wall into the shotcrete, on the left, and then similar on the right.
These might have been from Mongolia, because Mongolia had similar construction like this.
Ah, okay. Okay.
They use precast floor planks, usually untopped.
I was going to say or Sichuan, but I don't think we did any work there. There's a lot of school buildings like that. Yeah.
Yeah, not ugly, beautiful.
URM walls, well, they're very brittle, as we said. There was a lot of testing done in the early 80s, maybe late 70s, when engineers started attacking the URM problem here. And, we kind of came up with kind of prescriptive H/T ratios. I used to have all those memorized. I don't anymore, but if the span of the wall exceeded the allowable H/T, it was likely to crack and fracture and probably collapse. So here's one of the methods to strong back the walls, to stiffen the walls a little bit so that they would not do that out of plane. This shows a steel tube, which is very, very effective. We did a lot of stuff in the South with wood, because I think John Cariotis, part of the ABK group that developed a lot of technology, they had an approach that they really kind of wanted the wall to rock but not collapse, so that the wood post was a little bit more flexible, but there was prescriptive or calculated stiffnesses you wanted to get out of your strong backing system. So it was pretty trick. I mean, it was kind of very simple stuff, but it was kind of complex in the analysis and the thought that went into developing some of these systems.
So this that example there is an example of adding bracing for that slender wall in the form of vertical posts, and like the California Existing Building Code Appendix A1 has some prescriptive guidelines that say they got to be like, I think it's something like 10 foot on center. The alternative is to reduce the unbraced height of the wall and adding a horizontal element. Mm-hmm. And so that horizontal element, it might span between some verticals like this, or it might have bracing up to the structure above, some diagonal bracing. So this is one way. I don't see this way done as much as reducing the effective height, but this is certainly one way that can be done, and it's in the California Existing Building Code.
Yeah, true story. Yeah, I think I did a bunch of URMs back in the late 80s, early 90s, and I think I only did this once. Either the H/Ts worked out reasonably well, because they're not very tall buildings generally, or you put a horizontal brace in because it doesn't take space. You see a lot of those. So good stuff. Here's another method similar to what we talked about in the concrete, where you would actually add fiber wrap or FRP to either increase the shear strength or the out of plane bending capacity of wall. This is a little more high tech, a little more expensive, and probably a heck of a lot better than some of the other methods. That there are many ways to skin this cat. So. Actually, let me go back to that. This is kind of trick too in figuring out what to do with the piers too, because you can actually let the piers rock, and there's a way to analyze that, and you don't want them to rock too much so they're unstable, but rocking in piers is generally a good energy distribution system if it doesn't fail. And I don't really know where the balance point is. You probably hit it pretty quickly. Another little trick to be sure you have girders or trusses in these type of buildings. Always want some kind of resupport, some more positive support rather than just hanging off the walls or hanging off a ledge, as is shown here, where the wall decreases. You lose a wipe, and they would bury the girders on the top of the out through the inside wipe that gets cut back 4 inches. There's not very much positive anchorage, so you always want a redundant system there so your building doesn't collapse if if your wall becomes fractured with shear. And that load needs to be carried to the ground too. So diaphragms are always another challenge in URM buildings, or for Charles, maybe we say UMB buildings. I think in San Francisco they call them UMBs. Is that right, Charles? instead of URMs?
I thought it's still called URM, but URM.
Well, I know when San Francisco developed their provisions, which were about, I don't know, a good 15 years after LA, they kind of rebranded the whole thing. They didn't want to do what LA was doing, which is kind of funny. So they came up with a new name for it, and I don't think it really stuck because I think URM is more prevalent. Anyway, but typically in these buildings, you know, the roof sheathing would be just 1x straight sheathing, and the floor sheathing would be 1x diagonal. The diagonal sheathing, you know, if my memory is correct, we'd get like 400 pounds per foot of shear at ASD level, and the straight roof sheathing, you could get 100 pounds per foot of shear. So don't quote those in context with the loads we're using, because we were using rather reduced loads too at the time. But you know, this thing has evolved quite a bit. But one of the tricks is to either add some kind of horizontal truss to strengthen the diaphragm, or really behave as the diaphragm and ignoring the sheathing, or rod bracing or something like that. And I've certainly done some of those. But that's another thing you need to be attentive to. And this is an example that I was kind of mentioning, you know, like what we were looking at previously, where there's concrete planks, you know, spanning from beam to beam or something to something, and there's no real connectivity between the planks, where they're untopped concrete planks. So what this is showing is either, you know, using a steel plate to tie the two planks together to get some kind of shear capacity between the two, or, you know, in the example on the right, kind of ignoring that and adding a horizontal truss or some kind of element that will be able to transfer the shear. And in the middle of that, there's also a connection plate too that splices those two together. But it's something you need to think about. I mean, you could also FRP these, and maybe the next slide shows that. Obviously it does. So yeah, this is the same thing. We're strengthening the joint with a FRP connection between the two planks as you go through the whole diaphragm. Another very good trick. Another feature of these buildings, you know, they were pretty much, you know, if you go through Old Town Sac, I think we've probably retrofitted, I don't know how many buildings down there, a lot, I know for sure. There's a lot of old URMs down there, and they're pretty much all retail spaces or some kind of commercial space on the first floor, and then a lot of times the upper stories, it may be residential, they may be office space, it may be something different, but you know, the front facing the street is almost always completely wide open, and a certain collapse hazard, because there's really no shear resistance at all on that lower level facing the street. So a trick you'll see is, you know, adding some kind of brace frames or moment frames or some kind of system to you know, mitigate that soft story. I suspect this is one of ours. I'm not sure which.
Yeah, this is in up in Eureka. This one Bob and I worked on.
Oh yeah. Oh yeah. Okay.
Yeah, and the thing about moment frames is that the deflection criteria is really stringent for these buildings, because they don't want them to move a whole lot. So moment frames tend to get pretty expensive, but it's fairly common if you don't want braces.
I know. Yeah, Lon's right. The frames are just stupidly big. But a lot of people want the open windows. So I know you walk around San Francisco, you see a lot of very funny brace configurations in windows. You know, they kind of fit them in where they could. And, you know, the older ones clearly were, you know, prior to Northridge. So, you know, even the bracing that was put in at the time is probably suspect now. The old ordinary concentric brace frame systems that we've kind of moved away from, and that we wouldn't use for a building like this today. You know, I think, you know, Lon, we've done a bunch of friction damper type work in buildings like these too, prior to the BRBs becoming more prevalent.
Yeah, I did a one or two like that. We have it's either a 6 or an 8-story building up in Eureka. Same building owner of the professional building, 511 F Street. We built our own friction dampers based on some steel tips guideline.
Nice. Talk about creative.
Yeah.
Creative engineering. That's good. And this is just a detail, you know, one of the possible ways to connect the frame, you know, your frame beam or your brace beam. to the wall, because you have to collect the load into that, obviously, and you want it to not fail out of plane. You need to provide some stability to it too. I would also expect to see some bottom flange bracing somewhere along that beam. That's a moment frame or a brace frame, which, as we all know, is rather hard to connect into a wood diaphragm if you really want to make it work, but something you need to think about. It's kind of the same thing. It's really just showing the, this is for reinforced masonry, actually, where you have something that's a little better material, a little better known, where we use adhesive anchors. I know when I was doing URM, for URM, I don't think you can use any kind of adhesive. You'd have to grout or do something that's not so viscous, because in the brick buildings, there's a collar joint between each of the Ys, and you can always tell a URM building because like every 7th course, bricks are turned perpendicular to the wall, and you'll just see the end of the bricks. They use that to tie the Ys together back in the old Mason days. So if you don't see any soldier, and those are called soldier courses, if you don't see those in your building, it's probably not a URM. It's probably reinforced brick. And as I was saying, you're typically not allowed to use an adhesive anchor unless it's in some kind of a screen or some kind of system, especially for that, because the epoxy will just run down into the collar joint, and you'll just be pumping epoxy into there forever, and you'll really never get the adhesive to the material that you're looking for. And here's my favorite thing is the shotcrete. Either for in plane or out of plane. Or one of the favorite things. I don't know my favorite, but it's certainly a simple way to do it. Same with FRP. FRP can be used for both in plane or out of plane. A little more exotic material, but if you don't have space, it's a very good solution. Again, this is kind of same details we saw 2 weeks ago with the tying together the FRP. These are kind of boundary elements or additional flexural, elements at the end of the walls, and they get tied together through the floors and the old splayed hairpin type things. So again, here's kind of an FRP type attachment, either attaching plank to plank, like we were looking at the precast planks, or something like that, or maybe this is a collector. We could create out of FRP if we need to provide a big tension tie. That stuff works quite well externally applied to the concrete. This is Lon's building. This is 555 cap. This is kind of an interesting. Everybody in Sacramento has probably been here and seen it. It's I want to say 22-story building. There's actually two buildings. I think they're identical. They're right in downtown. Yeah, 2 towers are similar, not exactly identical. Early 70s. They're found to have a very tall first story, kind of a soft story, probably also a weak story, because they're 17 feet at the first floor and 11 feet floor to floor, above that, which is pretty short, but that's not unusual for concrete office buildings. Gravity system, 2A slab, blah blah blah, columns and concrete columns and pile foundations. You can see this isn't the ground floor, which is the taller floor. Perimeter moment frames, concrete, probably somewhat ductile moment frames. So the Sacramento team did a whole bunch of analysis on this. They had a lot of good things going for it, at least above the soft story. The soft story was the biggest deficiency in response. The beams were lightweight concrete. It ties at 13 to 18 inches. Wow, that's pretty. I didn't pick up on that previously, but and the beams were eccentric to the column. So it's had some captured columns in the West Tower as well, which there's some pictures of that too. That's kind of interesting. This for a while, for a period of time, people were using lightweight concrete for structural buildings, more and more because of the weight savings. The material is more expensive, but they thought there was some savings in the seismic and in the foundation systems and all the systems, associated with that. That kind of went away because the lightweight concrete doesn't really perform quite as well, especially when exposed to weather for long periods of time. So we may see that for buildings done in the 70s. I don't know if it made it into the 80s. Maybe it did early, but not terribly deep. So here's the eccentric beam to column connection. Again, like I said a couple weeks ago, this is kind of back in the day where we had some very good engineering tools, but not a lot of very good engineering tools, and we didn't have as much of an understanding or completely understand the demands and the desire to have ductility in our buildings. It's probably that time when these things were all calculated by hand. Shears and moments were developed, and then reinforcing was added to suit without additional thought of beyond yield state. So a lot of stuff like this happened back then. I think this is the captured column kind of detail. As you can see, there's a vault on the first story. I presume that's the first story. Then it's surrounded by, the column is surrounded by the vault walls. So there's some better pictures of all that stuff.
This was kind of interesting. They showed it as a gap around the column, but in actuality, there wasn't one. It was poured up, tied up against it.
Yeah, which is a bit of a problem.
Pretty dangerous condition, because that one column was captured by that vault. And the vault was really, you can see here the concrete, this part of the concrete, they cut the whole vault back. And so what you're looking at is they put in some steel plates. Those are steel plates to kind of close off the vault. And you see the lid of the vault and a wall beyond. So I think they're like 18-inch thick with 4 mats of rebar for security.
They didn't just abandon the vault, Lon? Could they have abandoned the vault and got rid of that?
No, there's a bank in this floor, on this side of this tower has a bank on a tenant on the ground floor.
Yeah, I don't think I've seen a vault like that in a long time. When I first started working, we did some banks and we would do the same thing.
Now they're using steel plates, right?
We do 3 layers of 5s at 12 each way, and they're all staggered, so it'd be really hard to saw through there. Anyway.
Our Hogue building.
Yeah. Oh, is that like that?
Yep.
Oh, geez. Yep. So here's a whole bunch of technical mumbo jumbo, site seismicity, and all this, and blah 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 blah. So Lon, sounds like this building was in escrow when the Napa earthquake hit, and then they got a little.
Yeah. So the building shook pretty good, even though it's kind of far away from the Napa Valley, but it's a taller building, so. And so it's got a higher period, and those seismic waves come from Napa, and then they hit the alluvial soils in the Sac Valley area, and they get amplified and for taller buildings. And so the building moved quite a bit. They had a lot of non-structural damage. No, not a lot, but they had a moderate amount of non-structural damage. Mostly, this building is got 4 or 5 different buildings that are interconnected with seismic joints. And so movement happened at the seismic joints. And so the carpets buckled and doors stuck, things like that. So the actual seismic joints worked pretty good. But they, obviously raised eyebrows, and they had to do some cosmetic repair. But anyway, so it was an escrow and for the new buyers. And so the bank, they have engineers that evaluate their risk, and they gave it a higher PML. And so the developer called us and asked us to do a study and how to reduce the PML so that they can drop the lender was going to require earthquake insurance. And so they asked, how do we get rid of their earthquake insurance? You lower the PML. So that's how that's how the whole thing started. And Amir was kind of he originally did some of the original study work before SAC kind of took it over for the production. But yeah, that's kind of what started the whole, it was like a perfect storm, which led to a nice opportunity for us.
Yeah, and a very good project.
Yeah, it turned out really nice.
Yep. So here's some more of the technical mumbo jumbo and a nice picture either out of ETABS or something we came up with. Anyway, I won't belabor you with this, but period, over 2 seconds. So almost 4 seconds in the first mode, which is a pretty long period. I guess that's about what you expect though for a 20-some story.
Only 14 stories though.
Oh, it is? Oh,
Yeah.
I thought I saw 22 in here. I'm sorry. I was reading something else somewhere. Clearly, I spent days and days and weeks preparing for this presentation that I didn't put together, but you know me, I'm happy to go through it and talk about it and give you all my opinions. So let me stop there and say any opinions are my own. So make your own engineering judgments. But you know, this is the seismic drift ratios, you know, prior to the fix. You know, much over 2% at the first floor, and you know, it gets very normal, you know, up above the second floor where the floor to floor heights are, you know, 11 feet, and it's a little bit more regular. But this is, I mean, this is kind of a problem. So that obviously that building wouldn't fare well in a design basis earthquake. Anyway, so what I think, I presume this is Amir's work, but you know, he's finding hinges were forming, and you know, a lot of issues where there wasn't really hinging capabilities in the detailing. So, you know, obviously those kind of drifts wouldn't be tolerable, you know, for this building. So then the target was, you know, to try to limit the drift to 1.5% at the first floor, and then things would clean up. So the solution was really just to add dampers at the first floor, you know, calm down that soft story and make it work a little bit better, and you know, control the drift that way. So you know, we've done this on quite a few buildings. I really like this approach because it works very well. And in this building, you know, they were able to get it significantly improved by just doing work on the ground floor. Here's kind of a plan layout of the dampers. You know, we put them in the corners and seem to work out very nice. I think this building is in one of our brochures where you see some woman at a coffee stand or a coffee shop, and
I think the picture's in this presentation, isn't it?
Okay, yeah, it probably is. I probably haven't scrolled through that far. No, I did. So here's the stuff we use for design, blah, 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 a bunch more technical mumbo jumbo. You can read this if you want, but the result after we added the damping in, you know, the drift ratios do less than 1.2%, you know, at the first story, which is actually pretty good. So worked out really good, and it took out all the plastic hinging in the beams where it wouldn't be able to tolerate it. You know, if we probably couldn't have gotten that all out, we probably would have done something else to increase the ductility, but you know, luckily we didn't have to with the addition of the dampers. So that's kind of a really nice thing. Here's kind of the comparison of the drift ratios, you know, before and after. On the left is the black with the squares is prior to adding damping, and the blue, of course, is after adding damping. You can see how significant the drifts came down. The same thing on the right, you know, as you go through time histories of what the drifts look like as a percentage of the story height. So pretty good project, I would say. Pretty good success. 8 fluid viscous dampers total. You know, that's not too bad.
That was for 2 buildings.
For 2 buildings.
Oh, that was each building.
No, that's each building, yeah.
Yeah, eight per
for each direction, each way. So that's pretty good. It's a pretty cheap seismic retrofit if you're all in. You know, here's some of our plan details, which are just beautiful to us. You know, here's some elevations of in the bottom left, I think is that captured column area. And there's a little bit more detail about how that all worked. Where's it, the bottom left? Where it's in this picture here, where you can see where that became somewhat of a concern.
This is a little bit of a hot mess. This spot here is where they added a mezzanine level, and so they had at some point they had retrofitted that, made the beam deeper. They had a door in there, and so it created like a stiffness irregularity. So we basically freed up the beam column joint. I forget the details of it, but we wanted to release that connection to avoid failing. I forget what I think it was, we didn't want to have the fixity in the middle of the column, because then it would be stiffer than all the other columns. So I think that's what this detail is all about.
Yeah, and I like it because it would have picked up all the shear in that whole line, or a significant amount of it. It would have fractured quite quickly.
Yeah, the captured column, I think, is like 1 bay over. So I think it was on the same elevation. So this one wall line had a whole lot going on.
Yep. And we added some FRP. It looks like 2 to the columns, in the potential hinge zones to provide a little bit more ductility. And here's kind of the connections of the dampers, into the concrete, which I really like this detail because, as you know, if you're trying to connect this stuff, what we did was we basically, added more concrete and connected into the new concrete. And I like that a lot because it's really hard to post install anything like this into existing concrete. And I think Lon will correct me if I'm wrong, but, and some of the other things we've done in the past is add actual steel columns to provide the connections and, not get so worried about trying to connect to existing concrete because it's darn near impossible. But this detail looked like it worked out, quite well, I would say, as far as, being consistent and being conforming in what's there already and being compatible. So yeah, I think this is a really good solution in my opinion. So hats off to the guys who did it, or the team that did it, not the guys, excuse me. Anyway, some more of the details about that. The tie configuration of the column at least looks pretty decent, for the time.
One thing we did too was we corrected the eccentric connection of the beam to the column. We only did this at the base with the dampers, but it's better than nothing.
Right. Yeah, you would definitely not want to put that damper eccentrically into the column. Anyway, here's some construction pictures, kind of what it looked like. Oh, there's that little short column that got wrapped on the top left. And then just more of the work.
Yeah, the reason that was wrapped is because they had changed the tie spacing to they had nice tie spacing actually they had pretty good tie spacing in the hinge regions on the top and bottom, but the middle was really quite wide spacing. So we added those to provide the confinement.
They just use D/2 or H/2 in the typical
something like that. Yeah, something like that.
Yeah, I did a lot of buildings like that back in the day.
Yeah.
Because that was the standard of practice. That's kind of what everybody did. We just didn't know better.
Yeah, we only need the FRP there on the second floor as well. It didn't go any higher than that.
Okay. Thanks, Mike. But pretty simple stuff, not hard to construct.
Yeah, the nice thing about the concrete is that you can just drill those dowels. If you hit a bar, you just move it. Yeah. Dowels don't really care. You don't have to coordinate with bolt placement or hole placement on the plates.
Yeah, very true. Hey, what's the picture on the bottom left?
It's just
a drive beam.
Yeah, we added a. Oh yeah, because these are pile foundations, and the piles weren't really very well interconnected. I think this is where we also added collectors at the foundation to distribute the load, the resulting load because you get a concentrated force at the base of a column if you only have dampers at certain columns. So that we wanted to distribute that reaction to multiple to the whole line of piles.
Yep, makes perfect sense. And that is at the ground floor. I can see the cars outside, so that's probably not hard to do either. It's just slab on grade. More construction pictures. You can see the embed plates in the widened concrete column sections. So pretty cool looking construction. Pretty clean, actually, I would say, given the amount of messiness that this really is. Here's a picture with the dampers installed. The beams ready for concrete, it looks like. Columns already concreted in. And there's our glamour shot that we see in every brochure.
See how they sloped the bar top on the right? to
Yeah,
emulate-
yeah.
that was their design statement, I guess.
Well, they also have to protect people from walking into that stuff if it's so low. If it's below a certain height, you need to provide a barrier, to something for people
Yeah,
like me to not bump their head on it.
Yeah, that's a good point.
But I like, I do like the looks of these things, and personally, I wish all this stuff was always exposed. The architects usually have different ideas, but if it's something this cool, I think they're probably totally on board with it.
Yeah, they wanted it as marketing. That's the
Yep.
outside of it right there.
Yep. Yeah.
They ended up replacing notice they replaced all the glass on the bottom floor
Yeah.
and with clear glass for a number of reasons, but they also like the idea of showing the dampers.
Yeah, it looks nice. I think it's a good move. Now we can be architectural critics, but yeah, it's definitely an upgrade. So at the end of the day, they saved $144,000 a year in earthquake insurance. So probably didn't take that long to pay for the retrofit. If it's $800,000 per building, that's a pretty darn good deal. 6-year return on investment. Yeah, good move. Move on their part. We're probably lucky that the Napa earthquake hit when they were in escrow, right? Or we probably never would have touched this job.
Yeah, possibly.
So discussion points. Yeah, we did a good job of fixing it up. Very limited scope, essentially given the size of the building and then what the whole retrofit costs. So I would say it's a very successful project. Yeah, kind of stuff we already talked about. So that's it. Questions, discussions, comments? Feel free.
Hello, Jeff. I have a couple of questions from Istanbul. Hi, Lon. Is that the building I have seen in Sacramento, or is it another building recently constructed?
No, that's the building in Sac. We've been there for dinner. Usually, a lot of times if we're in town, all of us will go sit outside. There's an outdoor restaurant there. Am I correct?
Yeah, when was that constructed?
It's funny that's been going on for decades. I mean, it seems like decades. They just, I think they just finished up a portion of it just like last year, maybe even this year. I don't know, Mike, you haven't heard anything on it recently, right?
I see. Another question. I have noticed that the PVDs were preferred. Generally speaking, are you also carrying out a feasibility study to determine whether PVD is more efficient or friction dampers are more efficient?
No, we didn't look at friction dampers. We just right to the fluid viscous damper here. I couldn't say why we might have approached it that way, but I think we have a high level of confidence in the viscous dampers for this application, so we went with what we knew.
Because sometimes the building may require stiffness, so that in those circumstances, friction dampers can be more efficient.
Yeah, that's a good point. We actually used a viscoelastic damper on another project, Hotel Stockton, where we needed the additional stiffness. So Taylor Devices, they developed a damper that was basically it had actual stiffness incorporated into it that was parallel to the damping. I don't know how they. I mean, I don't know how they did it off the top of my head anymore, but they added some. I believe they added some some sort of friction pucks or something inside of it to give it some additional stiffness. But it was kind of a new thing for them. Yeah, that was a way of adding stiffness and still using the fluid viscous dampers. Friction damper might be, certainly might be a good approach as well, but it's not what we did here.
Yeah, I understand. Yeah, thank you.
I'm just thinking, just in general, like, friction dampers and fluid viscous dampers behave that quite differently. Like fluid viscous dampers, they, have the most force when you have the most or the least displacement, whereas friction dampers are kind of behave more like braces. So it's,
Yeah.
there's kind of a big difference in how they behave. So it's not like a one-to-one comparison.
Yeah, it affects the dynamics. Certainly it will, the viscous damper will tend to reduce the response through, it'll dissipate some of that response and shift the period a bit more. The friction damper might attract a bit more force because of the added stiffness. So,
Yeah.
and also frictional force is a constant force throughout, the force deflection diagram looks a lot different.
Yeah, I agree, but they behave in different phases.
Right.
In Turkey, we have retrofitted a few production facilities with friction dampers because the structure itself was suffering the absence of stiffness. So that's why we have to prefer friction dampers. But when we consider viscous dampers, they become too expensive compared to friction dampers.
That's what I would expect. Is that a cost issue? Yeah. The thing about the viscous damper too is as Wayne said, they're out of phase with the elastic forces on the building. So your maximum force is you have essentially close to zero elastic force in the building when your viscous damping force, your dynamic force is the highest. Yeah. So by the time your building's fully deflected, your dynamic force is zero. Because you have zero velocity and they're velocity dependent devices.
Yeah, exactly. Thank you.
Amir knows a lot more about it than I do. And of course he does. He's our corporate engineering stud. And he could tell you a lot more detail about that. But and actually a shoot's pretty darn good now as well. A shoot's our Nepal liaison that's in the Sacramento office. He does a lot of the preliminary damper sizing for us now on our damp projects.
To my knowledge, in U.S. practice, there are not many shear walls in the existing buildings, but in Turkey, the structures may be too stiff to take the advantage of the energy dissipating devices.
Yeah, right. They're not as effective in a rigid or shear wall building. That's correct.
Yeah.
Yep.
Maybe more effective to use shotcrete on those buildings,
Yeah.
or more shear walls, right?
Yeah.
In fact, on one building, we did have a shear wall on one end of a building. It was a Citizen Hotel, and I think there's others as well that aren't coming to mind right now, that were causing some torsional stiffness in the building, and we softened them. We basically cut vertical slots in the wall to make it act like a whole bunch of little piers, made it reduce the torsional response and reduce the stiffness.
Yeah, that's a good approach too. I think we're actually
that's just where it was out of tune. It was out of balance. It was only on one end, and so it was appropriate for something like that.
Mm-hmm. We're doing something very similar at a building in Santa Ana right now that we're doing a feasibility study for. Or I say we, I would really say DuPont and Tracy's team in Saul in Mexico. He's done a lot of really good modeling. We're going to cut loose the really irregular parts and try to make the building a lot more regular.
Are we doing modeling in our Mexico office?
We are, yeah.
That's cool. For the high performance models?
Mm-hmm. Yeah, I don't know if is Saul on? He's our new PhD in Mexico City. He's a young, very bright guy, very good to work with. He's done a lot of good work with us so far, so I'm very happy.
Very cool.
Yeah. Lon, I have a question. I remember Stockton Hotel that was also retrofitted with PVDs. And since, as far as I remember, it was a URM building.
No, that was a concrete building.
That was
Yeah.
a concrete?
Yeah, and that's the one where we did the viscoelastic dampers.
Yeah.
Yeah, it was highly torsional, that one.
Yeah.
Okay.
That's Lon and Kit's presentation at SEOC got me excited to talk to Kit and join Miyamoto. Way back
Well,
when.
and Wayne and let's see who else from the San Diego office. Jonathan were at the convention where I presented that 555 cap that we just watched at the end. That was a SEOC presentation in, I think, San Diego.
Good recruitment tool. Obviously it works. Anyway, is that it? I think no more questions. I think we're good. All right. So thank you everybody for attending and paying attention and having a good discussion. I think this discussion is probably more valuable than any presentation I would give, but it was a nice presentation put together with a lot of good topics. So very much enjoyed. So thank you, everyone.
Okay, talk to you later.
Nice.
Thank you.
Thank you.
Thanks,
Lon.
Jeff.
Thank you.
Bye.
Have a nice day. Bye-bye.